Good morning, students. So last time we were discussing the infinite quantum well, in which we calculated the wave function E and corresponding E, the wave function psi and corresponding E. Okay, so this is what we discussed in the last class. And as I said, in reality there is no infinite quantum well. In reality, as such, there doesn't exist any infinite quantum well. It's a model out of which we can calculate the discrete energy levels and corresponding wave function and the probability density, and we can get some ideas about the finite quantum well. Of course, finite quantum wells exist. These finite quantum wells nowadays they play major roles. The present LEDs, even sometimes LCDs, laser diodes, lasers, then photodetectors, sensors, some optical devices, they are all made up of quantum well devices, quantum wells. So in reality, quantum well exists, but infinite quantum well doesn't exist. But this is the model. We can get some ideas, we can get some results, so that we can get the whole ideas about the realities. So this is what the idea behind. And this is about a single quantum well. So we are going to look into today about the same thing. We are going to get the wave function psi, corresponding eigenenergy value E, and probability density function in square quantum well. This is a single quantum well. Here the barrier is infinite. Here the barrier is finite. So this is the height of the barrier. So here your V0 will be infinite. Here V0 exists. V0 will have maybe around 200 MeV, 2 electron volt, 500 MeV, so something like that. So we have a height here. Height means we are talking about the energy. Okay, here potential height or barrier height, it represents an energy. It means we have to give more energy to cross the barrier. So that's why it termed as barrier height. Okay, it is not height merely doesn't mean that it is meter or nanometer. It is not like that. So it is in terms of electron volt. We have to give more energy to cross the barrier. It means, so that's why it's termed as barrier height. So this is about a single quantum well. So single quantum well in which the electron or a particle inside, it is confined within the quantum well. It is confined within the quantum well. And of course this is well width. So this is well width that varies from minus A to plus A. So electron can move in a well in 2 dimensions. So this is something like that. We know already about the electron in the bulk material, so which moves in all the 3 directions. Suppose we are going to keep a quantum particle here, it can move in all the 3 directions in the room. Suppose if you are going to confine only one direction, so this is in 3 directions, correct? So this is one direction, this is another direction, this is another direction. Suppose we want to confine only one direction, if you are going to restrict one direction, so the particle will try to move only in a plane. It cannot move in the Z direction. It cannot move in the Z direction. So particle can move only in the XY plane. This is something like well in the villages. So it is restricted due to the height. Some wells will be more height, some wells will be less height. It is restricted. But we can swim only XY plane, correct? So this is something like that. So we have an electron which moves only in the XY plane. So that's why it is termed as a well, quantum well, restricted in another direction. Similarly, you can restrict in 2 directions so that the electron or a particle, quantum particle can move in one single direction. So it's called a quantum wire, quantum well wire. You can restrict in all the 3 directions so that the electron or a quantum particle cannot move in all the 3 directions. What we call this as quantum dots. So quantum wells exist, quantum wires exist, quantum dots also. Put together we call this as low dimensional semiconductor physics. Sometimes we call this as nanophysics, reduced dimensional systems. Nowadays quantum dot lasers are very famous. Of course we have heard about quantum dots made up of LEDs. No? LEDs are made up of quantum dots. Quantum dot lasers are available. So quantum dots nothing but a pixel. It's a pixel on the LED screen. So quantum dots are very famous. Even we can make solar cells using quantum wells also. Okay, so it is very famous nowadays. So here the particle will try to move in the xy plane. So one direction is confined. For example, here the particle is confined in minus a to plus a, correct? So we can restrict. We can change the size of the well width. We can change the size so that the particle will move in the xy plane. Okay, so this is xy plane. Okay, the electron or quantum particle will move here. This is restricted. Okay, in this direction it is restricted. And this is about a single quantum well, and multiple quantum wells also exist. In fact, the more reality is multiple quantum wells, where in which we can have multiples of single quantum wells. See, all you have single quantum wells. This is called superlattices. So multiple quantum wells are called superlattices. So we can say that this is a square quantum well, and this is also a square quantum well. Need not be a square quantum well. So this is your well width. This is barrier. So barrier problem we are going to deal in the next class. Okay, barrier problem. So this is your well. This is barrier. This is well. This is barrier. Look at the size. All are equal. So they are all square quantum wells. Suppose if they are not equal, barrier is not equal to well. It's a rectangular quantum wells, multiple quantum wells. It's a rectangular one. Need not be always in this category. It can be also a parabolic quantum well. Okay, or sawtooth or corrugated quantum wells, V-shaped quantum wells. So many shapes we can have. Doesn't matter. You will not have always square quantum. Doesn't matter. So we can have many shapes. Okay. Then more reality lies in this picture. We know that atoms. So these are all lattice points. Most probably you would have studied in SSP, solid state physics, about the lattice points. Okay, so they are all considered to be atoms. Okay, atoms are in more potentials, in which electrons will move periodically in the potential. Okay, the nucleus itself have a strong potential. Okay, now you consider this is a nucleus. You just consider it's a positive one. Consider it's a nucleus, and this is the movement of the electron. So this is called a potential energy diagram. So this is your potential energy diagram, and of course we know the potential energy diagram. The formula for potential energy is nothing but minus E squared by 4 pi epsilon naught R. Okay, so we know already. So your V of R is directly proportional to minus 1 by R. So that's why it is termed as in the negative axis. Minus 1 by R. So 1 by R varies. This is 1 by R variation. So at 0, you just observe your V of x will be infinite. See? Be infinite. For the next one, again at 0, the V of R will be infinite. So this is a potential energy diagram. Okay. So now, and look at these lines. They are all 1s, 2s, 2p, 6. They are all energy levels, in which permitted levels, in which the electrons can exist. So allowed energy levels. So they are all allowed energy levels. So if we want to find out the electron somewhere, then we'll have to use the idea of probability. The probability of finding the electron in a particular place. Correct? Usually. Electrons are associated with wave. So waves also will have the nature of probability. Electrons are moving in a periodic potential, just now I said. Correct? The probability of finding the electrons also will be periodic. Okay? Similarly, the wave function also will be periodic. Is it okay? The electron is periodic in nature. The electrons are associated with the wave probability. So that also will be in periodic in nature. So we have to use periodic function. We cannot use ordinary wave function. We have to use periodic wave function. Periodic wave function, which we will look into the next class, which is nothing but periodicity multiplied by the plane wave equation. Periodicity multiplied by the plane wave equation. E power ikr, e power ik is the plane wave equation. So we'll have to use Schrödinger wave equation, use this wave function and get the energy. That energy also will be in periodic in nature. So we started with the electron, waves, probability, and we got the result that energy also in periodic in nature, correct? So energies, all the energies in the atomic array, they are in periodic in nature. So we'll have to approximate now to calculate to single quantum or multi quantum. We'll have to approximate. So this is a reality one. The approximation is something like this. See, this is our approximated potential. This is a reality, correct? So these are all realities one. So they are all approximation. Why should we go for approximation? Because Schrödinger wave equation for a single direction it is easy to solve. For 3 direction it will be very difficult. For number of particles in a solid to solve Schrödinger equation will be very difficult. So that's why we will have to go for the approximation method. So we can solve Schrödinger equation analytically, numerically which will be very easy, because just we are going to feed some numbers in the computer, we can get some results. So numerically it will be very easy. Some approximation also method also it's very easy. So these are all approximation methods. So that's why approximated potential. So square quantum bell or rectangular quantum bell, which we are going to see in the next class, this is something like Kronig-penny model. So they are all approximated potentials. The reality is this one. They are all approximated potential. So out of which we can get some energy and we can compare the energy. Okay. So this is what the quantum bell, the introduction about the quantum bells. In fact, they are all, suppose if we keep superlattices in which each and every quantum bells exist, correct? If they can overlap or they need not overlap. Suppose if they overlap, this wave function will overlap with this wave function. Okay. For example, you have a wave function, single wave function, so isolated quantum bell. You have a single wave function. If joined together, 2 quantum bells they join together, then this wave function will overlap with this wave function. So we will get 2 wave functions, 2 energies, correct? Suppose number of wave functions are there, number of quantum bells exist, then we will get number of wave functions, number of energy levels. All these energy levels they will overlap and they will give band energies. So bands. Okay, so this is the idea about infinite quantum bell, finite quantum bell, of course multi quantum bells, the reality, the array of atoms which are arranged in the solids. Okay, so out of which this is very easy to solve, simple one. It's a quantum bell. We are going to discuss today the psi e and probability density function. So we are going to get the wave function and energy eigenvalue. We are going to solve Schrödinger wave equation and get psi and get e. So this is the idea about single quantum bell. Okay. So this is one-dimensional square well potential. So particle in a box. Particle in a box or particle in a square well potential. Particle will move only in a single direction. Okay, so that's why it termed as. Quantum well is a potential well with only discrete energy values. So we are going to obtain only discrete energy well, like we obtained in infinite quantum well. Okay, we are going to get discrete energy values. Wave function, probability density function and energy eigenvalues can be focused in any quantum well. So we are going to get all the 3. It gives a deeper understanding of atomic, electronic and chemical bonding and crystal structure. Of course, if we know the results, we can get some ideas about the atomic structure, electronic structure. We can get the efficient electronic and optical properties. Okay, rather studying bulk materials, if you study quantum well materials, the properties will be enhanced. The property will have more efficient. The well width lies between here minus a by 2 and a by 2. So which we are going to see the diagram. The well width lies between minus a by 2 and a by 2. Lies between minus a by 2 plus a by 2 in the x direction. Okay. So V0 is the depth of the well. So your height will be V0. So this is the illustration of the quantum well. Okay. This is a finite quantum well. Just look into, you have a barrier. This is your barrier. It's a finite quantum well. This is your well. Okay. Well lies between minus a by 2 and plus a by 2. Okay. Now all the particles are associated with the energies. Now you consider the particles which are coming from left to right. You consider above the quantum well, there is no barrier height here. Barrier height lies only up to here, correct? There is no barrier height here. So energy of the particle will be more than that of your barrier height. So I can differentiate now these two. Here the energies are more than the barrier height. So energies simply they will go from left to right. Okay. So this is from left to right. They will never care for the potential barrier. Simply they will go. So if it crosses from left to right, this will have a continuous energy. It's not bound. It is free. Okay. It's free. It is not bound. It is free. So we will have a continuous energy. But here in this case, the energy is less than that of a barrier height. Okay. In this case, the particles, some particles will penetrate into the barrier. See, this is your barrier. Particle will tunnel into the barrier. It will go inside. Again, it will come back. So this case is called a bound state, in which we are going to have only discrete energy levels. We are going to look into later. So they are all discrete energy levels. Okay, it is not continuous. It's bound state. Okay. So now you just have the particles which are associated with the energies. Just now I said the wave function in this region. So we are going to divide three regions. This is the first region, second region, and third region. The potential inside the well is 0. Very important one. The potential outside is V0. The potential outside is V0. It means the barrier height in the region, first region and third region will be your V0. I repeat, this is first region. That one is the third region. The barrier height will be your V0. This is your V0. In barrier 2, what is V0? V0 equal to 0. V0 will be minimum. So we are going to assume that V0 equal to 0. Okay. So in the first region, the wave function, as I said, the wave function will penetrate. Okay. So we are going to have the solution of the wave function, which we are going to see later, which is nothing but a e power k1x. K1 is the wave vector. It's associated with the energy. Okay. So a e power k1x. And here in this region, it's a linear combination of cos and sine. And also it's different. K2. This is K1. This is K2. K2 is a wave vector inside the well. And of course, the wave function will die out. Correct? The wave function will die out. So that's why this is termed as d e power minus k1x. So wave function will, exponential will decrease. Exponential will increase. Here the combination of sine and cosine. Linear combination of sine and cosine. Is it okay? So particle moves in the x direction. So this is what the picture says. Any doubt? Any doubt on the picture? Okay. So we have two categories. As I said, E is greater than V0. What we call this as scattering. It's infinite. Okay. It's not bound. It's a free particle. Waves are infinite, continuous. They move from left to right with the momentum. Root of 2m E minus V0. E is greater. V0 is lesser. So that's why we have termed as 2m E minus V0. Of course, we know that E equal to P squared by 2m. Okay, E equals P squared by 2m. So P squared will be 2m E. So P equal to root of 2m E. So here it is outside the well. So E minus V0. And this will have degenerate values. For a single wave function, we will have single energy non-degenerate. For many wave functions, we will have the same energy degenerate. So this is called degenerate. We will have many wave functions, the energy will be the same. Okay, we will have a particular energy, and that term is known as degenerate. And this is your transmission coefficient, and this will be your reflection coefficient. For in this case, when E is greater than V0, there will be no reflection at all, only transmission. The particle of energy that will go from left to right. So this will have only transmission. So there will be no reflection. So R will be 0 and T will be equal to 1. So totally put together that will give you 1. So we know already E equals P squared by 2m plus V0, since E is greater than V0. So you just bring this term this side, E minus V naught will give you P squared by 2m. That's why P equal to 2m E minus V naught. So equation 2.18. So this is about E is greater than V naught, this is scattering one. So now we will go for the bound problem, which we are going to have. Okay, this is very important. This is our syllabus. So waves are finite, discrete, non-degenerate. For each wave function, you will have energy. So this is non-degenerate. Here it is degenerate. Here non-degenerate. They move with the momentum root of 2mE because V naught equals 0 inside the well. So that's why it is P equals root of 2mE. Here is root of 2mE minus V naught. Here V naught equal to 0 inside the well. So that's why momentum equals root of 2mE. So with the momentum, the particle will move inside the well. Now with the momentum, the particle will inside the well. With the boundary, A is greater than A by 2 and A is X is less than minus A by 2. Okay. So within this region. In this region, it is periodic, bound, but not degenerate. We are going to look in. Okay. So we can find the eigenvalues if we know the potential and the boundary conditions. So we are going to use the now boundary conditions. So before that, your V of X equals V naught when X is less than minus A by 2 according to the picture. Here it is V naught. There it is V naught. Here V naught equal to 0. See, this is what condition is. Your X lies between minus A by 2 and plus A by 2 is equal to 0. X is less than minus A by 2, X is greater than A by 2 will be V naught. So this is the description of the potential. Now we are going to use one-dimensional Schrodinger equation in the first region when X is less than minus A by 2. So this is your Schrodinger equation. Kinetic energy plus potential energy equal to total energy. So this is your wave function. Phi1 is the wave function, E is the corresponding energy. Okay, so this is the first region. In the second region, your V naught will be 0. In the second region, there is inside the well. Inside the well, V naught equal to 0. So Schrodinger equation in the second region, that is minus A by 2, X lies between minus A by 2 and A by 2. Okay. In the third region, when X greater than A by 2, again Schrodinger equation will be exactly equivalent. So this is region 3, region 2, wave function in the region 1. Is it okay? Now we are going to solve using boundary conditions. So boundary conditions, we are going to solve these two equations and we will be able to simplify and get the energy easily. So that's the idea. Now multiply the equation 2.20, that is equation 2.20. You just multiply with minus 2m by h bar square. So the first term will go like this and the second term will be exactly like this. I am going to bring the right hand side, E term to the right hand side. I have already multiplied with minus, so this will become plus. Okay. So in this expression, I have pulled 2m by h bar squared out. So we will have V naught minus E phi1. Okay. Look at this expression. V naught is greater than E. Okay, it's very important thing. Okay, V naught is greater than E. So inside the well, V naught. Outside E is greater than V naught. Okay, so V naught is greater than E. Now I can simplify this term 2m by h bar square V naught minus E, which is equal to k1 square. You just look into this dimension. It is of the same. So this is what I gave the assignment in the last class. Okay, so you have so this will be your m. Okay, mass, dimension m, and V naught E, that will be your ml square t power minus 2. H bar square will be ml square t power minus 1 whole square. You just square it, cancel it, and you will get 1 by L square. 1 by L square is the unit of k1 square. So k1 equal to n pi by L. We had this expression in the last class. Okay, k equals n pi by L. So now you can simplify 2.24 into 2.25. Okay, so out of this you can write k1 square. So you have d squared phi1 by dx squared minus k1 squared phi1 equal to 0. So solving this equation, we are going to assume this solution, which is nothing but phi1 equal to a e power k1. You just differentiate 2 times and substitute here. This equation will satisfy. you just try, okay, as an assignment. Okay, you just try, you can try. So this is a solution. This solution only we have written earlier, correct? A e power k1x in the diagram. Okay, phi 1. So now we'll go into the next region, that is region 2. Okay, so d squared pi divided by dx. So this is equation 2 in region 2, minus h bar squared divided by 2m partial d squared pi, no, ordinary d squared pi in the second region divided by dx squared, which is equal to e phi 1, e phi 2. So just multiply with the minus sign, you will get this expression. Okay, your k2 will be root of 2me by h bar squared. The solution of this differential equation is this one. We had already seen this one in the last class. Solution of this differential equation will be the combination of cos and sin. Again, you just differentiate 2 times and substitute here. This equation will be satisfied. Okay, you also try. So we have this equation now for the second region, and for the third region, this is exactly similar to the first region. Okay, so we will have this expression for the third region, and the solution will be d e power minus k1x, because it's dying out. Okay, it's dying out. Exponentially it's decreasing. Okay, now we have the second region linear combination of cos and sin. One is cos, another one is sin. Both are opposite nature. Cos 0 is 1, sin 0 is 0. Both are opposite nature. Combination of these two will give you exponential. Okay, so we can say that both are in opposite nature. You just have it idea that cos of minus x. Okay, instead of x, I am going to write with minus x. Cos minus x, cos of minus x will be plus cos x. Sin of minus x will be minus answer. So one will give you plus answer, another one will give you minus answer. One is the odd one, another one is even. Cos minus theta equal to cos theta is even function. Sin minus theta, which is equal to minus sin theta, is odd function, which we learnt in mathematical physics. Okay, so this is the idea. Phi of minus x equal to phi of x is an even function. Phi of minus x equal to minus phi of x will be odd function. So we are going to separate region 2, the solution of region 2, that is separately cos x and sin x. And for all even function, we say that this is symmetric solution. For all odd functions, we say this is antisymmetric solutions. Okay, antisymmetric solutions. So this is symmetric solution and this is antisymmetric solution. So this is the solution, the region 1. Correct? This is part of a solution in the region 2. We have separated now. Symmetric solution. This is the solution in the region 3. Okay, region 3. That is, region 1 is nothing but x, which lies between, which is very less, minus a by 2. So x lies between minus a by 2 and plus a by 2. X is greater than a by 2. Okay, so that's a mistake here. X is greater than a by 2. So this is in the first region, second region, part of second region, and this will be your third region. And antisymmetric will be, we have taken cos, so now we have to take sin. So this is in the first region, second region and third region. So set of solutions for symmetric solutions, set of solutions for antisymmetric solutions. So now we have separated.